Okay, so Yuteng, I made you co-host. Is that working? Okay. Okay, I think there are no more people in the waiting room, so we have a slightly different setting this time. Can somebody confirm that you can hear me?
Yes.
Okay, perfect, great. So we have a slightly different setting because today we start a new topic and I need my computer for that. And so in the previous lectures before Christmas, I gave you an introduction about the methods that we need, the theoretical methods that we need in order to understand how order emerges in non-equilibrium systems. And we also discussed how order manifests in non-equilibrium systems. So now in the new year, we will look at the other side. We'll now introduce methods that allow us actually to identify order in experimental data. And of course, I'm not talking about a few data points here. We're talking about large, high-dimensional data sets as have become common in many fields of science, like social science, but also biology now. So to begin, let me share the screen. So I hope that works. So I hope that works. So actually, that was a lecture that I gave last year already. Yeah, and so can you see? You can see the screen, I hope, right? Okay, so just trying to get the meeting controls. Okay, doesn't matter. Okay, so I assume you can see the slides. Now let me just make them full screen. Yeah, that's actually from a course that I gave last year together with Fabian Rost, the course Data Science for Physicists. And today we'll discuss the methods that we need that actually allow us to identify order in high-dimensional data sets. And what do I mean with high-dimensional and large data sets? So this is one of the data sets that I showed you in the very beginning of the lecture that motivated partially this lecture. And this is a data set that was produced by collaborators in Cambridge. And in this data set, on the x-axis, you basically have part of the DNA. So in the DNA, you have maybe 1 billion or 3 billion base pairs, 3 billion base pairs roughly, in mouse and human. And in these experiments, for each of these base pairs on the DNA, for each of these positions, for each of these 3 million sites of the DNA, we can take a measurement and measure whether there is a chemical modification on the DNA or not. Yeah, and on the y-axis, we have different cells. So we can do that in individual cells. And on the y-axis, we have roughly 600 cells from a mouse embryo. So for each of these cells, we can take roughly 3 billion measurements here along the sequence of the DNA. So that means that we have a data set here that is typically a few terabyte in size and that has 3 billion dimensions. Of course, not all of these dimensions are really meaningful. But to start with, we have something that is very huge in terms of size. And now we need something, we need some tools, some computational tools to process such data sets. Yeah, so what we want to do is we want to start with these measurements that I just showed you. Yeah, for example, we measure, that's a biological figure. It's not so important to understand the details.
Sorry,
Can you
1 second.
change your slide? Because I think I only can see your first slide.
Which slide can you see?
Data science. Oh, now it's.
Okay. So how can we do that?
Now it's working, I think.
Now it's working. Go to the next slide. Is that working?
Is the second slide sequencing cells? Yes.
No, it's not. Okay. Let me stop sharing. Let me share desktop maybe. Okay. Can you see the title slide?
Yes.
Now the first slide.
The sequencing cells? Yes.
Yes, and now another slide.
Yes.
Okay, great. So I was talking all the time. Probably you didn't see this slide before here. Yeah, so this is what was on the x-axis here. On the x-axis, we have these 3 billion base pairs. And for these base pairs, we can make measurements on the x-axis. Let me get a pointer. Yeah, so we have here the x-axis, and this x-axis has these 3 billion dimensions. These 3 billion measurements for every base pair on the DNA that we can take. On the y-axis, each row on the y-axis is a different cell. And for each of these cells that are taken from a mouse embryo, we can take these measurements, these hugely dimensional measurements, in this case, a living embryo. Now, so these are breakthroughs that happen in biology, but also similar breakthroughs with similar detail. We can measure social systems, for example, if you think about the social sciences, social networks, and so on, where we have huge amounts of data that we would like to understand. Yeah, in this particular example of biology, we would like to understand how we can transform the top part of this picture here, where we take measurements that have lots of different dimensions. For this case, many different cells. You can do that with millions of cells if you want, if you have the money. Now, how can we transform these measurements into a physical theory of what's generating these measurements? Yeah, that's what we want to do. And to do this, we need to identify order in these structures in order to build a hypothesis. Yeah, this is how these kind of data sets arrive on our desk. So here you see tables that contain different bits of information. For example, on the top right here, you have a table that tells us where on the DNA we have chemical modifications. Now that has, in this case, 50 million rows. We have another table here on the top left that tells us something about the same position on the DNA. It tells us what is the topological structure of the DNA. Yeah? Is it compact? Yeah? Is it like a spaghetti ball? Is it more open or not? It tells us about something about how this DNA lives in real space. Yeah, then we have other kinds of information. You know, we can ask, for example, how is this particular bit on the DNA? What else do we know about that? Is there a gene in this region? Is there some other interesting stuff going on in this region? Now we can ask what happens to these genes. What are the genes doing? That's on the top. Is it different experiments again? Yeah, in these regions of the DNA. Yeah, and we then have, for example, information about these cells. Where are they located in the embryo? What were the cultural conditions of these cells, for example, and so on. Yeah, so now we have these high-dimensional data sets from different sources, and we now need to combine them to create a big picture that allows us as physicists to generate a hypothesis. Yeah. So, and this is an overview of this lecture today, and I have to make a shocking confession that we're actually using R in this lecture. That's something we're not using typically in physics, but in this case, it actually makes sense. It's actually suited, but the syntax of R is a little bit not what we're used to in physics. So I'll give you a quick introduction to R, to the language of R. And I assume that most of you have already learned programming in some kind of other language like MATLAB or Python or C. Yeah, so I'll just give you a quick introduction into the syntax of R. And then I'll show you what are the tools that we have available to deal with these large data sets that are coming up in science. Yeah, so what are the tools that we have available? What are the computational tools? And how do we select the tools that we actually want to use? Yeah, then the very important thing is to bring this data that has many dimensions in a shape that we can actually deal with in a computationally efficient way. Yeah, that's called tidying the data, to bring it in a specific format so that we can vectorize our computational or numerical operations on these data sets. Now, I'll show you once we've done that, how we can then perform very easily computations on these data sets. And finally, I'll end with showing you how we can combine these steps to produce data processing pipelines. And of course, we want to do all of this in an elegant way that is not, so to say, heavy in terms of syntax. We want to focus on the structure of the data, but not on what is actually on writing things in C or so, where you have like hundreds of lines of codes for a simple operation. Yeah. So this is the structure, and if you have time in the end, I'll show you something more on data visualization. Okay, so this is R, yeah? So most of you won't have used R before, so we don't use that in physics very much. R is, it's not better than Python or anything. It's very similar to Python in that it's an interpreted language. It's extremely flexible, so nothing is fixed in R. It's like you have a function that rewrites itself while you execute this function. It's called extreme dynamism. R is very popular in statistics. You probably have heard in this context. And it's very easy to include C code in R. So if you worry about speed, you can always write things in C. And that's also what we're usually doing. The main advantage of R is that there's a huge repository of packages available, particularly in data science, genomics, biology, and so on. And one particular thing that is actually of the most practical relevant is that it has extremely convenient and high quality plotting functions. Yeah, so these are the benefits of R. There are of course some downsides. The syntax is very difficult for physicists to swallow. I'll show you later why. And typically, because nothing is fixed in R, it's very dynamic. It's typically slower than Python in general terms. So you wouldn't use R to write a stochastic simulation or something like this. Yeah, but for the task that we're doing today, it's actually a very good choice. Yeah, so it's slow. R is typically slow, but the core functions are written in C. So once you rely on core functions or on vectorization and things like that, then it's very fast, but you have to know how to use it. Yeah, but taken together, there's no particular reason for not using Python for this. The only reason is that for the tables and for the data I showed you in the previous slides, R has been, so to say, the standard language in these experiments in genomics, and there are a lot of packages and a lot of libraries developed for these genomics data that are collected in huge repositories in R. And meanwhile, Python is catching a little bit up in this context. So, but that's why we're using R in our group. It's the context of genomics, these particular experiments that I showed you on the previous slide. So typically when you use R, you use it in a development environment, an interacting environment that you can download from rstudio.com. And then you have something that looks very familiar to you if you use MATLAB or Python. You have a notebook here, a little bit like a Jupyter notebook if you use Python, for example, where you can write code and where you then have also then directly the output of your code in the same window, in the same file. You can export HTML documents if you want. You have a console here to type in code. Now, and then you have your workspace, like in MATLAB, where you see your variables, and you have a window that is made for looking at help pages and looking at plots and other stuff. And I'll show you later, we're getting a little bit more interactive. I'll show you later how this works in practice here. But this is just how working in R looks exactly like working in any other language, actually. Yeah. So this is some basic R. So this is just to show you that R looks very familiar to other languages, actually, in many respects. And before I do that, let me just show you what these boxes here mean, and I'll share for that a little R window. So let's go here. Let me share the screen again. Okay. Now you should see an R. Now you should see this RStudio window. Yeah, so this that I just showed you, and here we have the code. Now I can run the code. I can click on these little arrows here, and then I run a certain chunk of code. Now I can run this if I want and load some data, and I have a console down here that allows me to type commands if I don't want to use these notebooks here. And if you look at the bottom, I can now assign a variable here, A, and set it to 1 with these weird assignment operators. I can set A to 1, and if I press A, I just type A and enter, then I'll get this output, the value that is stored in A. I can also output more complicated values like this table here that I already loaded, and that I can look at this in the console. And this console output is now what you see in the slides. Let me open the slides again. Can you see the slides? Are we back? Are we back with the slides?
Yes.
Okay, great, perfect. So it's working. Yeah. So here we have this. I mean, I've made this fake console here in PowerPoint. Now this is just to show you it's basically the same as many other languages like Python. So here I call a function, and the arguments are given in these brackets. Let me give you a pointer. Here we go. So somebody wrote in the chat that the text is very tiny. Was that related to RStudio, to this development environment? Yeah, probably yes. Yeah, so we don't rely on that very much. Yes, the RStudio. Okay. So that's good to know. Okay, so just to show you, if I type like a function, I would call a function in R. I do it in the usual way. I can give different arguments to this function. In this case, I take a normally distributed random variable, and I tell R to give me 5 of them. And then I have some parameters that I can identify by names. So the parameter mean I set to 1. And the parameter standard deviation, I also set to 1. Now, these parameters have names, sometimes they have names, and I can call them with their names. That's very convenient. So if you have a long list of parameters and you don't want to give them all. I also can write my own functions, and that looks a little bit like in C. So here I define a function that's called mySum. And this function has 3 parameters, A, B, and C. And C has a default value 1. Yeah, and then this function returns a value that is just equal to the sum of these 3 arguments here, A plus B plus C. Now if I call this function, I set A to 1 and B to 1, and C is 1 by default, so I don't have to state that. I only have to state that if I want C to be a different value, then this function returns the value of 3. Yeah, just like in any other programming language. Yeah, we also have loops, of course, in R. Yeah, so this is a for loop, where you can, for example, have a loop that goes from 1 to 5, and then I can print something out or so. I have a while loop. So while some condition is fulfilled, or we want to print something, typically in R, you don't want to have loops. So if you have a loop in R, that means that you're doing something wrong. So these loops are slow because R is slow. And if you have such a loop, then it means that you didn't vectorize your operation, that you're doing something bit by bit that you could also do in one step. Typically, if you have a loop, then there's something wrong with your code. So that's you're very extremely inefficient. And so I guess I'll have written like many thousands of lines of R code in my life, and I have had exactly one loop. And in these many thousands of lines in several years, and this one loop I used for a stochastic simulation. Now the mistake was that you would never write a stochastic simulation R, but I did that because I was very lazy. So if you use these loops, then there's something is wrong, because these loops are very, you can typically replace them with much more efficient operations. So these are the standard constructs that you have in any programming language. You also have the if clauses here, like if the value of I is smaller than 5, print hello, and otherwise print not hello. So that's just also like in any other language, and you use these curled brackets like in C to define the scope of a certain frame of the code. That's should all be very R. Now, where things get a little bit different are the data types of R. So R has standard data types. So for example, here we can define vectors. In principle, everything is a vector. Well, that's the most simple data type. Your A, for example, the vector A, we define with this C here. Now that's a little bit strange. So in MATLAB, you would have... Pardon? Was that a question? Probably not. Just repeat it if it was a question. Okay, so this is just a vector. How can I go back in the code? Yeah. Okay, so this is a typical vector. We use the letter C to create such a vector. That means combine. And this vector has the elements 1, 2, 3. And we can also put other stuff in this vector like this NAs. That's for example, a measurement that is not available, that didn't work, for example. It's very convenient to have a representation on the computer for measurements that didn't work, for example. We can also have a vector of other types. So here this is a string or character vector of M and Fs, so that we can define this in the very same way. And we can access elements of such vectors with these squared brackets. Yeah, like in C, for example. But others, but unlike in C, we start counting by 1 and not by 0. Yeah. The next element is a list. Then the next data type is a list. Yeah. Then now it gets more interesting. A list can contain several elements of any type. For example, a list, elements of a list can be vectors. Now, for example, if I want to make a list, and the first element of the list is our vector A, and the second element of the list is our vector B. Now, they have different types, but we can nevertheless put them together in a list. And then I can access these lists here, these list elements by their name. So I gave it a name, number, and gender. And if I want to access the first element, number, by name, then I just use these dollar signs here. And I can also access this first element by its number, then I use the double squared brackets. And that's not so important, just to show you that these data types exist. When it gets more important for statistics is that we also have categorical variables. And that's something probably you don't know from MATLAB or C. I don't know about Python category. So we have here a vector that saves the gender of something, of somebody. Yeah, so we have a long, and then so suppose we do this measurements like 100 million of times, yeah, and then we have males and females, and in principle we could store the words male and female 100 million times in the memory, but that would be very inefficient. What we could do instead is to say, okay, I have a variable that can only take 2 values. Yeah, so I need just 1 byte at most to store these, which of these 2 values a given element has. And then I save, in addition to that, I save labels to these 2 values. Yeah, and that's what a factor is doing. It's a categorical variable that can only take a limited number of values. For example, this vector B here can only take 2 values. And I tell R that this can only take 2 values by making this a factor. Now this category variable is called a factor. And when I look at this factor, F here, then it gives me the output, now MF, MF, MF. Yeah? And it tells me these levels here. These are the typical values these elements can take. Yeah, and if I want to make these levels or these labels of these 2 values different, I can call these 2 female and male, yeah, by changing these levels. And then I can output this again and have male, female, male, and so on. So what happens here in R is that still internally, I don't use any more memory, although the strings are longer. What I changed here is a lookup table of R, where R looks up where these 2 values, how these 2 values my vector can take, are called for any plotting or any printing purposes. Yeah, that's a factor, and it's very efficient if you think about, for example, biology, for these measurements that I showed you in the beginning. You have these hundreds of millions or billions of measurements, and you have 200 million measurements for chromosome 1. Now you could either write in your memory, have a vector that has the element chromosome 1 200 million times. Or you just save a number, an identifier for chromosome 1, and give it a label, like this one here, with a real name in a separate table. Then you don't have to save the string chromosome 1 200 million times, but only once in this table where you look up what is actually the name of this factor level. So there's a very efficient way of saving variables that appear very often, but can only take a limited number of values. And that's then called a factor. Now that's the data type that you're probably not familiar with. Yeah, and then we can go on. Yeah, and we can now go to data types that can really store the data that we're looking at. For example, experimental data. And the simplest way you can do that is called in R a data frame. A data frame, Python also has data frames, and as far as I know. So these data frames are nothing but lists of vectors. So remember the lists. This is a list. It can save any kind of element that you want. And if each element of this list here has the same length, then we can interpret this list as a table. Yeah, and this is what we do in these data frames. So here we have three vectors, x, y, and z, and they have different types. So this is a numerical vector, this is a character vector, and this is a Boolean, so logical vector. And we now can create this data frame and say that the first element is x, the name of the first element is x, and the second element, the second column should be y, and the third one should be z. Oh, sorry, I don't know why this is happening all the time. The third one should be z. And what you can see here is how this is then represented if you look at the output of such a data frame. So here's the first vector. That's now the first column in our table. The second column is on our table is this one. And the third column of our table is the Boolean vector. Now this is a data frame. It's essentially the R version of a table. Yeah, and internally, this data frame is basically a list of vectors that have the same length. Okay, so this is a data frame. And this data frame looks close to what we could be dealing with, or is actually what we could be dealing with, or sufficiently general to allow us to store any amount of experimental data. Now, like a table is a general way of storing data, and these data frames are essentially tables, and they allow us to store any kind of data that we might measure. Now the problem is, now we have this data table, but what, as I told you in the beginning, in these data frames, I told you in the beginning that we actually have data that is terabytes in size. So now we need a way of performing operations on these tables in a very efficient way. So that we need the right methods. And how important that is to pick the right methods is here on the left-hand side. So here you can see these bars, and these bars are time measurements that it takes to perform certain operations on data sets of certain size. Yeah, and so here this is 500 megabytes of data, so a pretty small data set. And then you measure the length of such an operation here, that's denoted by the bar. And you can compare different versions, different packages that allow you to look at this data. So for example, one popular method in R is called dplyr. It's extremely popular and very easy to learn way of managing these tables. Another pandas is basically the Python version of such a data frame. And then we have here data table on the top, the blue one. Now, so this is a very fast C implementation of these operations on these data frames. It's very fast and memory efficient. So and then you have some things that are more used in companies, also in this list. Now but this all seems very reasonable. So we have here 12 seconds, 20 seconds, 90 seconds. Nothing of that stops us from getting a result. Now we increase the size of our data set to 5 gigabytes or 50 gigabytes. Still very small compared to what I've been talking about. So here let's have a look at these 50 gigabytes. Now suddenly there's a huge difference here. A lot of these packages, a lot of these methods here do not produce any result at all. Yeah, they run out of memory, for example. And some of them, like this very popular one, takes just a huge amount of time. While others, especially this data table method here, performs very well. Yeah, so we have here, what is that, 13 minutes, so that sounds reasonable. No, that's seconds, 13 seconds. So 13 seconds, so this was, sorry, so this was 0.2 seconds here at the top, and now we're at 13.5 seconds. So that sounds pretty reasonable. But if you go down here to these methods that we have here, so the 13 seconds is something that you can wait, yeah, in front of the computer and still have some interactive way of working. Now, if you go down here, of course, a lot of these methods just fail, but there's also some of them just take so long that any reasonable working, like this Dipler here, takes so long that any reasonable way of working with data is just not possible. Yeah, so that's why choosing the right method here is important. And also what's important is to look at how these methods scale with the size and the complexity and the dimensions of your data. So what this tells us here is there's a huge difference. Yeah, and actually what I did when I was a postdoc, for example, like every physicist, I used MATLAB. I was used to use MATLAB, yeah, and then very quickly, almost immediately, MATLAB failed on such operations. Yeah, and then when these genomics methods came up, yeah, I used the red one here, Dipler. This is extremely popular and very easy to get into. It's very flexible and very well documented and so on. And I used that, but then experimental progress moved on exponentially. Yeah, so when I started, I was looking at like data of a few hundred megabytes of size. And at the beginning of this talk, I showed you data that were like a terabyte of size. Yeah, and very quickly I ran into this problem here that I wasn't able to get any results at all in meaningful times. So at some point I had to rewrite all my code, and what then turned out to be a reasonable choice for really large data is this data table package. It is R version, and also the Python version, as you see here, is not much slower than that, than the R version. This data table is written in C, it's very fast, and if you stay strict to it, then you can expect a performance that is not much worse than actually C, but with orders of magnitude less programming work. So today I'll use this data table package here, and I will also introduce some concepts here that are applicable to any other of these methods or any other way of dealing with data actually. Okay, so let's use this data table package. Yeah? So it's very fast and works for extremely large data sets. The downside is that this syntax is not very friendly for beginners. Yeah, it's a little bit cryptic, it's very condensed and very compact. But it turns out that this, at least for me, was the only way that I could deal with data, like in an experimental field where the sizes of data sets are exponentially increasing. This was the only way that made me work in an efficient way. Yeah, so we start this data table, we load this package just by calling library data table. Yeah, and then if we have a data frame, we can just convert it to a data table by this command as data table. That's very simple, nothing else is necessary. So in this lecture, I would like to look at some real data. Yeah, so and this real data, I could now load like 1 terabyte of data, of experimental data, and but that would not be very efficient actually for this lecture, because it would be very slow and also very difficult to follow. So I'll look here at a simple data set, and we'll do some operations on this very simple data set. And this is actually a data set that any of you can download. And I'll also upload or share a link where you can download the code of this lecture that I'm using in this lecture and the data itself. Okay, so this is the data set. This is called New York City flights. And these are all flights that departed or arrived in New York City airports in 2013. Yeah, so this data set consists of several files, of several tables. One is the actual information about these flights here. Yeah, so we have for each flight, we have information about the year, that's 2013, but we also have information about the month, the day, the hour. We have an information about the flight number, an identifier of the flight. We can know where it came from, this flight. Now we have a tail number. That means that we can identify the airplane that was used, the carrier. So is it United Airlines, American Airlines, Lufthansa? And then we have some information about the delays in these flights. So delays in the departure, delays in the arrival, how long was the airplane in air, and many other bits of information. Now, this is the information for all flights. Now we want to interpret this information. That means that we need to connect this information to if we want to understand, for example, where these delays come from in this data set, we want to connect it to additional information. The one thing you might be looking at is the weather. Now, if you ask for why is a flight delayed, we can look at the weather. Yeah, and this weather is a different source of data. And for this weather, we can also get the time, the month and day and hours. We can look at the weather at a certain airports, at certain locations. We have temperature, humidity, wind speed, and other information about the weather at a certain location and at a certain time. Now we have information about the planes. Now we have this tail number here so that it identifies the planes. And then we can also download some information about these airplanes. Now we can, for example, look what manufacturer the airplane was made. We can look at the model. We can look at the year this airplane was built, the number of engines, the number of seats, the type of airplane, and so on. We can get some information about the airport, where we have airport information, an airport identifier, the name of the airport, the longitude and latitude and altitude of this airport, and so on. And finally, we can also get some information about the airline that corresponds to a certain flight. So, and now one thing you need to notice is that these tables here, they share information. For example, if we want to learn what the weather was for a given flight, then we can look at the year and the month and the day and the origin airport of this flight and look and compare that to the same columns in this other table here on the left-hand side that contains the weather information. If we want to learn about the airplane that was used, we can take this column here, this bit of information, the tail number, and compare that to the corresponding tail number in this planes data set and look what kind of manufacturer this plane was made by, which year it was produced, and so on. So these bits of information are connected by different variables. We can use these overlaps between these data sets to bring them all together later. But first, let me show you how to load data. And loading data is actually also not a trivial task. Loading data can take hours or minutes, depending on what function you use for that. And in the scope of R, the fastest functions are the ones from the data table package. They're called fread and fwrite, that allows you to write data. And they're basically parallelized versions of reading huge amounts of text data, of ASCII files. And it's very simple. You just use the command fread, it's called fast read, to load a certain file here, for example, the text file. And fread will do all of the rest that you need to do. It will identify the columns, it will identify the data types, and so on. Typically, you don't need to do anything. For example, we can read in this flights data sets here that contains the information about flights. And it's actually the flights that departed from New York City. And this is then how this data set looks like here. If you just print what is in, once we load these flights, we can print what is in and see what's in there. We have these different columns, like 2030, that's the year. Then we have different months, we have different days of the months, and we have departure times, and we have real departure times, we have scheduled departure times, and we have delays, we have arrival times, and so on. We have here carrier, we have flight numbers, the airplane, the tail number of the airplane, and so on. Origin, destination, and so on. And we have a timestamp here, a time signature of when this flight actually took place. Now, so let's go to RStudio and see how this looks like. Here we go. Now, this is RStudio. I hope you can see RStudio now. It should be still sharing. And so here at the top row, so this was a little bit small, right? Let me zoom in. Okay, so I hope this is better. So here we're loading all of these files. It's actually the same thing that we did, that I had on the slide. So for each of these different bits of information, we now load these files into memory. So I had already done that before. So here they are in the workspace, and now we can click on these files, and we can either now just type flights, and get this huge table out, or so you see we have here more than 300,000 flights that we have information about. Or I can just click on this file here and get a little nice table view of the data that we have. This is the flight information. It's also high dimensional, not as extremely high dimensional as the example I gave you, but it has still enough information that we cannot easily detect patterns in this data set. So this is the data. We have 300,000 flights, and now we can try to detect some structures in this data set. Let's get back to PowerPoint. Okay. Here we go. Now we've loaded the data. We've got all of these different data tables now, or data frames in memory. And now we're trying to make sense out of these data sets. The first thing that we always need to do is to bring data in a format that we can deal with it, the data. And this format is typically called tidy data, or long data, or long format. Now, there are two simple rules that you can use to decide whether a data table or a data frame or a table is tidy. So one thing you need to make sure is that every column is a different observable. Now, for example, different types of measurements. Every row are then different observations of these measurements, of these observables, or different variables. once you stick to these rules, your data is tidy. And when your data is tidy, so every column is a different observable and every row is an observation, then we can use vectorized operations in R or Python to perform operations on entire columns of these data tables. Yeah, and that first is extremely fast, yeah, because it's vectorized. We perform these operations one column at a time, and it drastically reduces the complexity of the code. Now, the data that I showed you are one of the standard data sets and data science, and that you look at for teaching, and this data is already tidy. So let's have a look at these flights. So every column is a different observation, a different observable. Yeah, for example, a different measurement, a different departure time, a different arrival time, a different flight number, a different time point. And every row is a different observation, so a different flight. So this data table is already in a tidy format, and it's already in a format that we can deal with. So we have nothing to do here. And a standard example of a messy data set that we also often find in physics, but also here in this case in genomics, is that we have matrices, that we share data as a matrix. For example, in this matrix here, that's a typical matrix here. So this is a measurement, one of these genomics measurements. So here on each row is a different gene. Yeah, so, and the first column here is the name of this gene. That's a very cryptic name. These genes have cryptic names. Yeah? Each row is a gene, and each column is a different cell. Yeah. So this data set is not tidy because the same measurement, so these numbers mean how many products of this given gene we have measured in a given cell. Yeah? So these are the numbers. It's not important to understand the biological context. And but this data set is not tidy because the same observable, namely the number of these gene products, is repeated in different columns. And you can easily see that by having this format, we're not very flexible. So if I now, for the same gene and for the same cell, make another measurement, what do I do? Where do I put that in this matrix? Yeah, so we have to have a separate matrix, and I have to live with separate matrices, yeah, in parallel. So this data set is not tidy, and I cannot perform easily parallelized operations on this data table. And now we want to make this data table tidy. I know there are special functions that allow us to do that. And these functions are basically, I'll just give you the names, and they have similar names basically in all contexts. To make such a data table tidy, like the one that I have here, this function is called melt. It's called, you also said you melt a data table. Yeah, and that brings us from this matrix format to a format where every column represents an observation, and each row each column represents an observable, you know, like a measurement, and each row corresponds to a measurement or an observable. Yeah, so what you see on the right-hand side, that would be the tidy version of the data that I showed you on the last slide. So the first column would be the cell. The second is the gene, the name of the gene. The second column would be the name of the cell. And the third column would be the value that I measure for the gene products. So that would be the tidy format. And now I can have a long vector here of numbers in this one column, and I don't have 200 columns as in the previous slide. Okay, so how do we do that? In R, this data table package, the command is called meld. We just give it the name of our data table, and then we identify ID variables. So these are variables that need to remain, so to say, intact once we reshape this matrix. Yeah, in our case, this is the ID column. Yeah, and the value name is how we want to call the values that are in these matrix elements here. And we just call this expression. Now that's what we call. And the variable name is the cell that we have here already that tells us that this variable name is distributed now into this column. Yeah, and then if you look at these colors here, you can see how this command distributes what is actually now distributed into several columns, how this reshapes this data table into something that has a longer format. It's actually also called long format, where we have the cell name in this column and then the corresponding measurements in this column for the gene products. Yeah, you can look at this. I'll upload the slides, of course, so you can look at this in detail afterwards. It's a little bit abstract, but this is, so to say, how we reshape data tables to make them tidy. Yeah, and we can also make them messy again. So I'll go quickly over that because that's not something we use. But sometimes you just want to have your good old matrix back because some function, some other package wants to have a matrix. Yeah, and that's called then, this function is called dcast, and that just reverses, the operation that I told you on the last slide, where we give you, where this function takes the data table, the name of the data table variable as the first argument, and then a formula of how the rows and columns should be now separated in this new matrix that we want to have. Yeah, it's not so important, so I'll not go into it. It's not so, we rarely use that. And now we have some tidy data. Yeah, so we have some tidy data now. Every column is an observation. Every row, sorry, I always mess it up. Every column is an observable or a variable. Every row is an observation. Once we're in this format, we can now have a very simple syntax. Yeah, and this syntax actually captures ideas that we also have in other, maybe more popular languages like SQL or so SQL. That's more that captures operations on this data table that are quite generic. So this is the general syntax that we use in this data table package. So we have three. Now we take this data table D, and in squared brackets we have three arguments. Yeah, and the way you read these three arguments is that you take the data table D, and then you have something at the first argument that operates on the rows. Yeah, you have here a condition that tells you which kind of rows you want to take. The second one operates on the columns. Yeah, and for example, you can, in the second argument, you can perform a calculation on the columns. And the third argument is a grouping variable. Now the third one is like a typical matrix statement, Y and J. The third one is a grouping variable where we can group rows together by certain conditions and perform these calculations here, group by group. Yeah, so the way to read that is to take the data table D, subset the rows using I. That can be some expression, some logical statement, for example. We calculate what is in J and do this calculation grouped by whatever is in this third argument. And I'll now show you step by step how this looks in detail. And these arguments here, these three arguments, are a very, very general way to also say parameterize operations on these large tables. Yeah, so with these just 3 arguments, we can do a lot of stuff already. And if you think about it, it's actually abstract, but it's very simple. So now first let's have a look at the very first argument. Yeah. Yeah, so let's just say we have a table and we just want to get a subset of rows from the table. Yeah, for example, we want to look at all planes that have 4 engines. Yeah, the way we do that is we just write this logical statement here as the first argument. So engines A equals 4. And if we do that, then we get back a data table that only has the planes that have 4 engines in them, that have 4 engines. Now we filtered the rows of this data tables for the rows that have the value of the engine column equals to 4. Now we can also select a subset of columns here on the right-hand side. And this we do by this notation here. This dot is actually a shortcut for a list. Yeah, so what we do is we give a list of the names of columns that we want to extract as the second argument. Yeah, so for example, we take this planes data set and we want to get the tail number and the year this airplane was built. And then we get a shorter, a smaller data table back that only has these 2 columns in them. Yeah, so this is all something that you could also do with any other package or any other programming language, of course. Now we want to get a little bit more complicated. Now we want to do an operation on these data tables, on these large data sets. And these operations in general have a quite general scheme. Yeah, so, and this general scheme is already in this syntax notation that I showed you a few slides ago with the I and J and the group is already, so to say, in there. So that the steps that we take is called the group aggregate combine scheme. So what we do, the general operation on such a data table looks like that we first group our observations by some meaningful way. So for example, we want to group all flights that happened in the same month. Yeah, and then we aggregate. Aggregate means that we extract all of these groups, all flights from the same month at a time. And aggregates mean as a third step that we perform some kind of summary function on these flights that departed in a certain month. For example, we want to then calculate the average temperature or the average delay. Now, this is the third thing here, where we aggregate all of these different flights that belong to the same group and calculate a single result from that. And I'll also give you now a specific example of this. Yeah, so what we can do, for example, is that we can group by carrier. So we might want to ask, are all carriers equally bad or equally good? Or is there one carrier that is worse than other carriers? Now, the way we do that is we first group, that's the last column here, we group all flights, and we take the flights data table, and then we group the flights, all flights together that have the same carrier. And for each carrier, we then calculate the average delay using the mean function. Yeah, we take the mean of the departure delay, and this third argument just tells us that we should remove NA, so not a numbers, for example, where not the proper measurement was taken, where this information is missing. Now we just ignore this. Yeah, so for every carrier, we take all flights and calculate the average delay time. Yeah, so this is what we do here. Now all carriers, that's here the grouping is the third variable. And then we perform this operation in the second variable because it operates on the columns. And the operation we do is we calculate the average of the delay, and we save it in a new column that's called mean delay. Now, what we get from that is for every carrier, we get one number, which is this average delay. Yeah, and you can see that basically that confirms what you expected already, that United Airlines is not performing very well. Now we can also have more complicated procedures. Now we can, for example, combine that with a subsetting in the rows. We don't want to take all flights. We always want to look. We only want to look at flights in the evenings, very late flights. And then we can, for example, do the same thing. And we can also have a more fine-grained, or we can look at different combinations of variables here. For example, in this case here, we take all flights that depart after 8 p.m. And the remaining flights we group by month and the origin airport. And we again calculate the average departure delay. Yeah. And now for every combination of month and airport, we get a value for the average delay here at the bottom. Yeah, for example, in January, the Newark airport had an average delay of 14 minutes. Yeah, and JFK was doing much better. Yeah, and so you can see that this also kind of is something that people expect to see here actually. Yeah. Okay, so this is how this group aggregate combine paradigm can be fit into very compact syntax on basically arbitrary complex tables. Now, we can also, so this was now a summary statistics where we summarized several rows, yeah, all flights that have the same carrier, or all flights in a certain month and a certain airport. We summarized all of these flights into just one quantity. For example, the average delay. So we performed a summary here. What we can also do is we can add a new column to our table that has one new value for each row that is in the original table. So we don't perform a summary. It's also sometimes called windowing for whatever reason. And so we have one new value for each row that we had in our original data set. For example, here, the top row, if I don't want to have the flights, if I wanted to have the speed in kilometers per hour, yeah, I can, for example, then calculate the distance over the airtime in minutes. Now that's the speed in miles per minute. Then I multiply by 60 and convert to kilometers. And then I have the speed for every flight. I have the average speed in kilometers per hour. I can also rescale, for example. I can combine these simple computations here with the grouping. For example, I can rescale all distances by the average distance of a certain carrier. For example, I can ask, is this flight much further or much shorter than a typical flight conducted by the same carrier? Yeah, so then I can calculate a rescale distance. That is just the distance divided by the average distance of this carrier here. And then again, I get a new variable, a new value for each row that I had in my original table. And the way I do these operations is by these symbols here, these defined symbols, column and equal signs. Now, the way this looks like is now that we have here our original 300,000 rows. But for each row, we have calculated now a new column, a new value that we save in a new column, speed, kmh. That is the speed in kilometers. And we also have the rescale distance. Now, for example, this flight here was a little bit 10% shorter than the average flight of this carrier. Yeah, and this also is saved into the new column that we've given these names here. Yeah, this is something that is also happening very fast and memory efficient. So now comes more complicated things. Yeah, so this was in principle easy step. We add more columns, we perform a summary, and this data table package allows us to write a very simple syntax in order to do that. Yeah, if you try to do these groupings in C also, you write many, many lines of codes to do that. Now, the next step, we want to make use that to get some more understanding about these delays here in New York City, we want to make use of the fact that whether we have different bits of information, and these different bits of information share columns or share information that allows us to link them. Yeah, for example, we can link the weather to a certain flight by matching the year, the month, the day, and the hour, and the airport. Yeah, and with this we can connect the flight to the weather that occurred when this flight departed. Yeah, we can also connect the airport information. For example, so this FAA is an identifier that has a different name in this table, but is essentially the same as in the origin airport. And we have the information to link these tables together. Yeah, the planes, the tail number is a unique identifier that allows us to look up the plane of our flight in this data table, this data set of all planes. And also the same with the airline, we can look up the carrier identifier in another data table and get the name of the carrier. Yeah, so these tables are interlinked, and now we need efficient ways to merge these different bits of information together. Yeah, and this merging happens in a way that is also often called joins. Now, this is a general principle that you do basically in any kind of data handling task, independent of the programming language that you're using. And the first join, and then you can perform these joins or these mergings of these data tables in different ways. And these different ways differ in the way which information you keep in case you only find it in one table but not in the other table. Yeah, for example, so let's begin with one kind of join. It's called the left join. That's called the left join. And what you do is that you keep all rows that are in the left data table, yeah, in this A here. Now we want to combine, in this case, the information in A and B. Yeah, and then we can look up, okay, so here we have a value x1 that corresponds to A, and we have a value of x1a, and now we can look up what is the other columns, x2 and x3. Yeah, so x2 is 1 and x3 is true. Yeah, and then we can combine these two columns in the right way that they correspond to the value of x1a. Same for B. Now we can look up B in both columns, so they don't need to be in the same position. In both tables, we can look up the B and get the values of the remaining columns and sort them here to the end of this table. And now we have the 3. the C. Now C is in table A, in the first one, or in the left one, but not in the right one. And a left join now means that we take C from the left one. We don't have information from the right one, so X3 is empty. And we disregard all rows that are in the right table, but not in the left table. So that's a left join. And in R, or in this data table framework, this is done by the function merge that takes two tables. And the left join is then specified by saying that all X, so all first column, all entries in the first column should be true, should be taken. There's also a short notation for this joining, and that's just when you index one data table by another data table. So it's a very compact syntax for performing a very complex operation. And this is something, these joins are also something that are not trivial computation. Think you're doing that with something that has terabytes in size. Yeah, so in principle, you have to look up all rows in both data table and find the corresponding matches. Yeah, you need to have very efficient algorithms to do that. Yeah, and depending on what you choose here, which package you choose to perform this algorithm, you can wait for days or you can wait for minutes. That makes a huge difference. So if there's a left join, there's also a right join, and right join just means that we keep all rows from the right table, but we disregard rows from the left table if they're not in the right table. That's the right join. And in R, this just is, that works by also by the merge command, and we just give the argument that all Y, yeah, that we should all keep all columns in the second Y data set. Yeah, and there's also then a short notation for these right joins. Yeah, there's a so-called inner join. That's the most restrictive join, and this inner join just keeps values, keeps rows where we have information in both tables. Now, if we don't have information in both tables, then this row will not end up in the final data set. For example, C only is in the left table, D is only in the right table, yeah, and then we none of these ends up in the final results. That's the inner join. Yeah, and so again, here there's a merge command for that. We just say all equals false, and there's also a shorthand notation with an additional argument for that. So in all of these commands here, I didn't specify the column that we should use for joining. I didn't specify that X1 is the column we should use for comparing. Yeah, I didn't specify, for example, if you look here, which column we should actually use to match flight to weather. And I didn't do that because this column has the same name in both data sets. So X1 pops up both in A and B, and then R automatically assigns these columns that have the same names, uses them to match these different tables. So if there's an inner join, there's also an outer join or a full join. And this full join retains all values from all rows. Yeah, so that it happens if we just now join or merge these two tables, then we get our column X1 that is shared between these tables, and our column X2 from this first table, where we don't have a value for D, and the column X3 from the right table, where we don't have a value for C. Yeah, so this retains the most information. Okay, so now we can do some merging. So now we can, for example, ask, are these delays affected by bad weather? Now, so the first thing we need to do is to merge the flights and the weather data sets. because they share columns with the same names, for example, time hour or so of our, where's the origin airport? Now, since I didn't plot that here, they share columns with the same names. They're the ones that are connected with these arrows. That works automatically. So I merge them. And now I have a new table that contains information about the flight, the carrier, and also the delay. But also at the same time, the columns from the weather data set that have information about wind speed and precipitation and about the temperature. Yeah, and now we can go on and ask, for example, let's group this combined table here. Let's group that on the one hand by the rows that have a wind speed larger than 30 and by wind speeds smaller than 30. Yeah. And then for each of these two groups, calculate the average departure delay as before. Now, so if the wind speed is smaller or equals to 30 here, then the departure delay was 12 minutes. If the wind speed was larger than 30, then the departure delay was 28 minutes, so much larger. And if I couldn't evaluate this condition here, for example, if I don't have information about wind speed, yeah, then I get also a value for these NAs, for these non-available data. Yeah, so that means that, if it's very windy, there's a higher chance, or there's a typical higher average delay in these flights in New York City. Now, we can also ask, we can also merge the flights table with the plane table. So is anybody stuck at the join slide? Now, so what is the slide that you're seeing at the moment?
Are planes equally reliable?
Are planes equal? So that's the right. So Matthew is having a problem. But at least some of you are seeing the right slide. Okay. Okay, so we can merge the flight information, yeah, with the information about planes. And now I give this additional column here, this additional argument. I tell the merge command to use this column tail number to match the information, to match the rows. Now, if I do that, then I get also my flight information about the delay, about the carrier, and so on. But I also get information about the manufacturer, about the model number, and about the year this airplane was created. And because we had already a year column, namely the year of the flight, we now have two different columns, year X and year Y. Year X is the column of the flight, when did the flight take place, and year Y is the year when the airplane was built. Okay, and now we can just do our calculation. Now we can ask, are certain manufacturers more or less reliable? Are the planes by certain manufacturers more or less reliable? Yeah, so that we do the same thing. Yeah, so we group by manufacturer. Now by this column here, we group now the rows. And then for each group, we calculate the average departure delay here and save it into a new column, mean delay. And in this case, we also calculate the standard error, which is just the standard deviation divided by the square root of the sample size. We can have two computations or as many computations as we want in the same row. And here we see that, okay, so we have here Airbus Industries. I don't know what, I forgot what is actually the outcome of this. Boeing is a little bit later than Airbus. And then we have here two times Airbus. And the problem now here is that Airbus apparently changed its name, and one of them is older than the others, and that's why they have different delays. Now, these are smaller airplanes here, like this Embraer and Bombardier. These are smaller planes, and these smaller planes have higher delays. Now, Canadair is also smaller. Yeah, and so the smaller planes seem to have higher delays. Yeah, and then we can also do a trick. Yeah, so typically you do many operations, and such a processing of such data sets, you do many operations after each other. Yeah, and what we typically do in programming, we do one operation and save the result in a new variable. Now then we do the next operation and save the result in a new variable. Now we do another operation and save the result in a new variable. Now this is very inefficient if you have long pipelines of maybe hundreds of different steps in your analysis and how you transform the data. Yeah, and in R and also in other languages, there are ways to chain operations after each other, to make these pipelines in a very efficient and condensed way in terms of syntax. So there's a way that is implemented in this data table package. There you just chain, there you just put these square brackets directly after each other. For example, here we create a new column, wind speed and kilometers per hour. And here we just multiply the wind speed in miles per hour by 1.61 to get the kilometers per hour. Yeah. And then directly in the next step, we group by month and calculate the average wind speed in kilometers per hour. So these are two steps, and we don't have to save the results and intermediate variables. We just put them down, we chain them directly after each other. So there's a more common way to chain or to make these pipelines. And this is in another package that's called Magrittr. Now we load this package just at the beginning of our code. And this package does one thing, it provides us with an operator, this one here. And everything this operator does is it takes whatever is on the left of it and passes it to the first, as the first argument to the function that is on the right of this operator. Yeah. So this is very simple. We take what is on the left and pass it to the function on the right as the first argument. Yeah, and with this, we can then have longer chains if we want. Now, for example, we take weather, calculate the wind speed in kilometers per hour, and then use this chaining this pipe operator here from this package and pass it to the next argument here. So we have here an updated data table with this new package. And that's what we take, and we pass it to the next step of our analysis, where we calculate the average wind speed per month. And we take the result again and pass it to basically any function that we want. And here we pass it to, for example, the head function. And this head function just gives us the first 5 rows or so of our data table. Now, so with these operators here, you can make very long pipelines, and you still have your codes in a very, basically you have a list then in your code, you have a list of steps that you perform one after each other. And so your code is still in a very convenient way that you can still understand. Yeah, so this is a more complex example of such a pipeline here. Now we take the flights data sets, yeah, merge it with the weather data set, yeah, merge it with the planes data, merge the result now with the planes data set, merge the results with the airports data set, And here I have to specify the columns, yeah, that because they have different names in both data sets. And we merge it with the airlines data sets at the very end. Yeah, and now we have a data set that has all the different information, all the different sources of information in the same table. Yeah, and now we can, for example, remove flights that don't have information about the departure delay. And we can do the steps that we did previously. For example, we can get the speed of the plane, the average speed in kilometers per hour. We get the rescale speed, so are we faster or slower than what is typical for a certain airplane model and a certain carrier. Now, and we can also calculate things like correlations. Yeah? So for example, here we calculate the correlation between the temperature and the rescaled speed of the airplane. Yeah? And here, what do we do here? So what do we do here? So we calculate the difference in speed of the airplane for flights that have a delay larger than 20 minutes and where the delay is 0 or smaller than 0. Yeah, so here's that's the difference in the speeds that have a large delay and that have a negative delay or no delay. And we calculate that by carrier. That's just an example here. And what we see here is that, so here this correlation here is typically positive. So this correlation is positive. That means for some reason, the warmer the temperature, the higher the speed of the airplane. Yeah, there's a positive correlation. So whatever this means. Yeah, and also what we see here is that this difference in speed is very often positive. American Airlines also is positive. That means that these airplanes fly faster when they have a delay compared to when they don't have a delay. Yeah, and you can also compare the carriers. United Airlines has a little bit more speed than American Airlines. And you can get all kinds of insights here from that. That's of course not extremely insightful, but it illustrates how you can do simple operations on complex data sets in just a few lines of codes. And I don't have to tell you that in C or MATLAB you would spend a lot of time and a lot of lines of codes to implement that. Yeah, just to summary this part, and if we have time, I'll show you a little bit about plotting. No, we don't have time. So I showed you that these data frames are efficient ways of storing high-dimensional data of different kinds. And depending on where your data is stored and how large it is, you can choose different tools. Yeah, if your data is stored locally and it's very large and you rely on speed, then data table is a good way to go. If your data is for example, on a server on the internet, and it's not that large, then you would use other codes that are better at interacting with network resources. For example, like this dplyr package. And the key step is actually always to clean up the data, to bring it to this tidy format. And once you've done that, we have this split, aggregate, combine paradigm where you group your data by different conditions, by basically any condition you want. And then for each group, you extract the corresponding rows of the data table and perform operations on this, for example, to perform summaries on this data, on these rows. And the package that I showed you here allows you to do all of these steps in a single, very short line of code. And finally, I showed you how pipelines actually help you to structure your code if it gets very complex, which is usually the case. And what I will do is I will upload some slides that show you how to visualize data. Now that's just, I mean, you all have your favorite plotting packages. I'll upload you some slides that shows you how to basically, how people developed a grammar for graphics that allows you basically to make an infinitely complex plots or data visualization using a very simple grammatical construct. So I'll upload this on the website, and then let me know if you have any questions. And otherwise, see you all next week. So next week, I should say, so next week we go into machine learning, and we'll have a guest speaker, which is our local, which is basically the chief data scientist from one of the Dresden institutes here from the Center for Regenerative Therapies. And he'll share, Fabian Ross, and he'll share some of his insights into how to use machine learning to detect then actually low-dimensional structures and high-dimensional data sets. Now, as you probably realize, now we're able to do computations, fast computations on huge data sets. But what I showed you was a little bit tedious. You know, this was, I actually didn't show you actually how to come up with low-dimensional structures or with order in data. Yeah. So, and this is something we'll deal with next week, and we'll have a guest lecturer then, which is Fabian here from Dresden. Okay, see you all next week. Bye. I'll stay online for a while in case you have any questions.
I was wondering if you dealt with like temporal data, or are most of the data that's coming out of these experiments just kind of, you know, there's some static information about the genomics and proteomics and all that?
Yes, so this typically static data, but although it's static, it contains dynamic information, indirectly. So you have measurements. So of course, like very often in biology, you have to kill the cells that you actually want to measure, or you have to kill the animals that you actually want to look into. And but you have some indirect dynamical information. I'll actually share. You sent me an email about a paper. We just uploaded something that actually answers your question about how this field theory and data science approaches work together. And this is actually an example from genomics. Okay. I share it with you in the chat. Just see where this is. Here we go. Okay, so I'll share it with you in the chat.
All right, thank you.
Here you go. And that actually answers the question in your email. I needed the Christmas holidays to have some time to finish and upload it. And this is actually an example where you have static data. In genomics, you can only have static data, but indirectly you have dynamic information. So actually, although in this specific example here, we have static data because of course you have to kill the cells, you have to kill the embryo, but you can still have time courses with different embryos or different cells. So that you kill one embryo at one stage. That's of course mouse, not human. So you kill one embryo at one stage, and then next embryo 1 day later. And the next embryo 1 day later. So then you get some implicit temporal information. And actually, in this same paper, we also conducted a time course with a very high temporal resolution, but you always have at each time point you kill, you look at different cells. That's always the that's the best you can hope for is something semi-static. But nevertheless, so we still have dynamic information indirectly via the measurements that we can make, for example, along the DNA. Yeah, and so that's, although we cannot make direct dynamic information, we can have indirectly generate hypotheses that we then can indirectly basically test using static data. If you have a look at this manuscript, you'll see how it works. And let me know if you have any questions. It's very a little bit biological. And this manuscript also has a supplement with all the field theory in it.
Okay, thank you.
Okay, great, perfect. Okay, so if there are no more questions, then see you all next week. Bye.